Hey everybody, in this video I'm going to help you navigate the periodic table as described in chapter 2. First off, each box represents an element, and the symbol for each element is either one or two letters. So H is for hydrogen, U is for uranium, and then we have some kind of weird ones like W for tungsten and Na for sodium. Tungsten was originally called wolfram in Latin, and sodium was originally called natrium. Note how the symbols with two letters have the first letter capitalized, but the second letter is in lowercase. The top number in each box is going to be the atomic number, which is equal to the number of protons in the nucleus of each atom. The atomic number also acts as kind of like an ID for each element. So if an atom has 92 protons in its nucleus, it's always going to be uranium. The periodic table is numbered according to this increasing atomic number. And the bottom number in each box is the atomic weight or mass, which is equal to the amount of protons plus the number of neutrons in each atom, since those have mass too. The reason that the atomic weights are not generally whole numbers is because not all atoms of a given element will have the same number of neutrons. The atomic mass is essentially an average weight for all the atoms for that particular element, and the number of protons will always be the same for a given element, but the number of neutrons can vary. So let's take a look at the periodic table. Our columns are called groups, and our rows are called periods. And if we move down a column vertically, our atomic mass and size are going to increase as we add more orbitals with electrons in them, okay? So those are going to increase. Now, as we go from left to right along the period, our atomic mass is going to increase because we're adding more and more protons to the nucleus. But our size is going to decrease, okay? And this is due to the positively charged nucleus exerting a greater control over the orbiting electrons. And this is going to pull them in tighter towards the nucleus. And this greater control of electrons is going to be referred to as electronegativity. So an atom that has a lot of mass relative to the other elements in its row is going to be smaller. And this is why fluorine is the most electronegative atom on the whole periodic table. It's a really small atom, but it's more massive than the other atoms on its row. And that's one of the reasons why fluorine really wants an electron. Fluorine, and we'll talk about this some in future chapters, fluorine is really reactive, all because it is extremely electronegative. So my tall groups on the left and right of the periodic table are going to be called the representative elements. So group 1 and 2, and groups 3 through 8, these are going to be called representative elements. Okay? And this short block here, these are going to be called the transition elements, or you may see them called transition metals. All right? And then this bottom row, or excuse me, these two bottom rows here are going to be called the rare earth metals. Okay, and in general, these are going to be radioactive. Okay, now we can distinguish elements as metal and non-metals based on this line that we have here, this black line that goes under hydrogen, between hydrogen and lithium, and then it stair steps down: boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Okay, so anything that is above this line and to the right is going to be referred to as a non-metal, and anything that is below and to the left, these are going to be called metals. Okay, and hydrogen, we'll consider hydrogen to be a non-metal because it is above that line. Okay, the only reason that hydrogen is on the left side of the periodic table is just to make it look symmetrical and pretty. Okay, now let's talk about each one of these groups real quick. Okay, so my group 1 metals, these are going to be called the alkali metals. All right, and the alkali metals are going to be pretty water reactive. All right, so if I drop a chunk of, say, sodium into water, I'm going to have a very caustic solution. Okay, I'm going to have a lot of heat being produced and some hydrogen gas, and I can see it have a violent ignition. And I have a few videos on the website that you can watch of sodium reacting. Okay, group 2, this is going to be the alkaline earth metals, and these have the same properties as alkali metals, but they're a little bit weaker. Okay, so they're still going to produce that hydrogen gas when they come into contact with water, just not as much. Okay, now group 3 through group 7, okay, these are, group 3 through group 6, these are just referred to as our representative elements. They don't have they actually have a wide range of properties. They don't follow a ton of trends like group 1 and group 2, or then group 7 and group 8, okay? But we can refer to group 3 as the boron family, group 4 as the carbon family, group 5 as the nitrogen family, and group 6 as the oxygen family, okay? Now, group 7, these are the halogens, and the halogens are the most reactive of all the nonmetals. Remember how I was talking a little bit ago about how fluorine is very reactive because it is the most electronegative element, okay? So the other halogens are also pretty reactive. These are going to be toxic, highly irritating to the skin, and they don't burn, but they're potent oxidizers, okay? Chlorine is probably the most common halogen that you will see out in the field, okay? Now, group 8, these are going to be the noble gases, and these are in the most stable configuration because they have 8 electrons in their valence shell, okay? That's something that we talk about a lot in the notes, and that's something that we talk about in the Bohr model video, okay? These have 8 electrons in their outer subshell or their outer orbit, and so these are going to be highly stable. You're really not going to see a whole bunch of reactions with those. All right, now the transition metals, these guys here in the middle, all right, these don't really follow all of the rules that we've previously talked about, and they're going to give up electrons, which we'll talk about more in chapter 3, but they're going to have the ability to give up a different number of electrons depending on what their charge is, okay? And if that doesn't make a whole bunch of sense, I promise you after chapter 3 it will make a lot more sense, okay? Now, the rare earth metals down at the bottom, these are going to generally be radioactive, okay? And some of these elements are going to occur naturally, really up until uranium. These are going to be able to be found naturally. Once we get past uranium, these are going to be synthetic, okay? And once we get over to 104 back over here, these are going to be synthetic as well, so they're made in a lab. All right, that's all I have for you for the periodic table. If you have any questions, let me know.